Yeah, if you're ready.
Yeah, it's a. I haven't waived the presentation.
What's that?
Meeting. I said I always ask for people to present. It's just a nice way to close the class.
Oh yeah, it's great. I have no problem with it. It's good with me. Can you see the slides okay?
This is perfect.
Okay, great. All right, well then let's go ahead and get started. So the project is machine learning for facial expression recognition. We're going to go try to go fairly quickly through a lot of this so that we can cover some questions at the end. And so if I seem to go too quickly over something, just let me know and we'll come back to some other slides. So the project, what is it and what's the motivation? So what is machine learning for facial recognition? So facial expression recognition is it's a computer-based method, computer program-based way to automate the recognizing and pairing of a given facial expression with its underlying human emotion. The machine learning component of this is that we use, instead of trying to find a precise function that maps inputs to outputs, we're using statistical learning methods and a large data set of pre-labeled faces and pre-labeled with their mapped human emotions, and then we're going to, using that, we work on creating kind of a, instead of a function, a filter, a sieve, or a screen, a grid that we can then use to sift any new unlabeled faces. And the idea is that they'll, with relative accuracy, fall into the right bucket for the emotion that should be mapped to them. Oh, this looks like it's going on automatic play. Just a minute here.
I do have a question here. Go to that slide.
The motivation?
Yeah.
Okay.
I have a question. Not here. Next.
Okay.
So did you find any applications in public safety law enforcement?
I've anecdotal things in the news about mostly China's what do they call it, the social credit system, as far as the using all the cameras and watching kind of the sentiment analysis of crowds and trying to avoid riots and things like that. I haven't seen as much in the West, but
Oh, wow.
I didn't do a deep dive on the public safety part yet.
Are you talking New York Times, Washington Post? Where did you see? Or just blogs or?
It was web articles, so it would probably be like I'd have to NPR, CNN, Guardian News.
Wow. Wow. Foreign relations diplomacy, is that?
Yeah, so the potential there is overlaps with the interpersonal. The last one on interpersonal will be language translation and interpretation. There's so much about language that is unspoken context. Even English, we're notorious for having one word that can mean a million different things depending on the context, and getting some of those nonverbal cues, especially the facial nonverbal cues, could potentially really improve the accuracy of not just like translation, but interpretation.
Also, did you find anything on stroke?
On strokes, these were.
You're thinking.
Yeah, this is more of my thinking. This is, just personal experience.
Correct. It's correct.
Um,
I'm working on stroke, but it will be very
oh,
fascinating.
really?
Yeah, well, probably 20 years. I can send you a bunch of articles, and we have an active project right now, but not emotional recognition.
Yeah. So I do have personal experience with caregiving of dementia, schizophrenia, and autism, and those are ones that when those illnesses, they, like everything, sometimes they're not so bad and sometimes they peak. It's not every day is the same. But when they do peak, a lot of times there's just something you can see in a person's face. They just, it's like they just have that look about them that something's not right. And if we could extend this given time beyond 7 abstract emotion, 7 oversimplified emotions to, things like this, or especially pediatricians and working with children that can't articulate yet, what's your pain scale, 0 to 10, or, yeah, it hurts in your tummy, but what do you mean? And, or maybe comatose or patients who may be unconscious, but they may still wear some of their condition on their face in a winch of pain, or maybe a surprise or happy look if they hear a loved one voice when they're in a coma or something like that. Something that might be worth noting that would otherwise be hard to pick up.
Yes, I agree.
I
love this slide.
Was that?
I love this slide.
Okay, great.
Yeah, your applications and your thinking is right on.
Thank you. Great. I love the project. It was really incredibly challenging, but it was neat to see something with so many cross-disciplinary, there's so many different ways this can bleed over into the arts and the behavioral sciences. And I mean, this easily extends outside of computer science really quickly.
Yes.
So I'm going to go just back one quick. Okay, yeah. So why do we care? It's more of what we just talked about. The only thing I would add is the return on investment. With so much of our communication being in the nonverbal and so much nonverbal prone to misunderstanding, from an economic perspective, it seems like you could easily make the case that for a small gain in accuracy or improvement in consistency, you should be able to translate that to a big payoff. So a relative, it's not, you don't have to solve the biggest world problem here, but small gains and improvements would go a long way in this field. So we talked about the use cases there. A quick little history. So I would call this like the pre-digital, history. And we've been coding emotions and interpreting facial expressions for thousands of years. Artists have coded them into ancient art, sculptures, masks, the Greek theater arts and the theater masks for a very long time. Then in the 19th century, end of the 19th century, take a more academic approach to it. And Darwin publishes the expressions of the emotions in man and animals in 1872 with an eye towards proving the hunch that these facial expressions demonstrating different emotions, his hypothesis was that this is likely a very universal human trait, regardless of culture, language, ethnicity, age. So he publishes that. Moving into the 20th century, Paul Ekman extends on that, publishes a very foundational piece on measuring nonverbal communications, and he becomes quickly well known for his work in deception detection. And the popular TV show Lie to Me, if you've ever heard of or seen that, is based on his work. Then in the late 20th century, even the marriage and family therapy world, the coding of facial expressions is getting used in academically to help build systems that can get troubled marriages or troubled families that want to learn how to communicate better with each other, get them on the right track. And there's a whole body of knowledge that's been built based on similar things in marriage and family therapy. So that's leading up to this is all analog at this point. Here in the present
Excellent.
age.
By the way, your background is excellent, sorry.
Oh, great, thank you.
And then your presentation too, I'm glad I asked you to present because I can see the genuine interest in your work.
Oh,
which is-
yeah, I love it. It's great. Thank
Yeah.
you. I really appreciate that.
Yeah,
Uh, So, going here into the post-digital age, there's been so much, in a compressed amount of time that's happened in even our lifetimes, but I won't go through all of it here, but I'll hit about 3 points that are really big. Bledsoe experiments with computers detecting faces. We're not talking about expressions yet or emotions, but we start with detecting faces. And then in 1989, Jan LeCun publishes his backpropagation method, which then becomes a major, anchor point for what is now deep learning. He was also, I think, heavily involved in the MNIST and the NIST data sets, the handwritten single-digit integers and things like that. And then more recently, some of the biggest, the things that have happened is that in 2015, Google releases TensorFlow as an open source technology. So, you're taking commercial interests and they're opening up things that would otherwise be proprietary. And similarly, in 2016, PyTorch machine learning framework is released. So just in the last, 6 or 7 years, there's been a huge amount of the gates have been opened to a lot of new tools.
I don't think LeCun invented backpropagation, but yeah, he did publish a paper. Okay, it's not his for sure.
Yeah, I mean,
Yeah,
I know that he's most well known for his work in the AT&T Bell Labs and the handwritten numbers and handwriting recognition. I'm familiar with him through that.
Okay. Yeah. His backpropagation wasn't his. I
Okay.
mean, but he did have a nice paper on it. You're right.
Okay.
Anyway, let's keep going. Yeah.
And as far as what's coming around the corner, and experimenting with some different combinations of methods, LSTM and reinforcement learning. But primarily, a lot of it comes down to more and more affordable access to things like cloud computing. In fact, part of this project, I ran some of it on Google's cloud platform, and they're really friendly and making things affordable, and a $300 credit to rent data space and GPUs in their systems. And then also just because of the explosion of social media and people interested in it, the availability of large data sets is getting better and better every year. So, just a quick summary of where we're at here is, what machine learning is not. It's not an exact science. We're not trying to get a perfect algorithm. We're not trying to make proofs and axioms. It's not going to be one size fits all. But what it is, it's an approximate, it's an estimator. It's a selection of multiple tools that you can take the approach to the same job. It's generalistic. So in that sense, machine learning is not deterministic. Machine learning is stochastic. So there's a sense of, a scattering of randomness about what the results, what we should expect to see. Like anything, before we dive into the models, it's important to understand the workflow of how we approach just getting started. And like anything, understanding and defining the problem is a big part of it. More so with machine learning, it's really important to give up some, to make some, when necessary, some gross oversimplifications, add some constraints. And one of the obvious ones in this case is, 7 emotions is, human emotions are more messy than that. I don't think anybody's making the case that there's only 7 emotions, but we try to distill it into something that we can work with, and then test it and prove it at this level, and then maybe as time goes on we can make it expand it. Likewise, machine learning is about predict. So we want to know predict what. So, and most often we're either predicting a quality or a quantity. In the quality sense, or a category classification is the thing of banana, apple, orange. Quantity, we're talking regressors, tell me a value. How much is the earth going to heat up in this year? How much Are these polar caps going to melt? And before we can get to those outputs, we need to know what we're looking for in terms of classes and labels. And if we know in this case we want 7 classes of emotions, we have to have a data set to work with that is already constructed in that same manner. So if you've got data sets available that map to what you're looking for, that's great. If not, then you have to be prepared to, wrestle with the idea of making a data set. If it's important enough, you may have to, go out and create a data set mapped to the classes or features that you need. And all of this has to be balanced at cost. Time, money, effort, it all has to, at the end of the day, it has to be usable in the real world, and that means money. So using, I've got 3 data sets here as examples that are already tuned to 7 labeled emotions for facial expression recognition. And they kind of range along a spectrum here from the JAFE, or the Japanese female facial expression database is relatively small. It's very consistent. It's a little on the older side. It's been around for a while. It's highly regularized. The images, not only are they all Japanese females of the same age, they're all zoomed in the same. They're have the same lighting, the same, face on. They're not posed differently. On the other end of the spectrum, completely, we have a large data set that was put out by Kaggle.com during a competition, if I understand, recently, called the Facial Expression Recognition 2013. On this end, instead of like 213 images in the JAFE, we're talking 30,000 images. The images are grayscale, but they're way more generalized. I mean, there's images of people with a microphone in front of their face, or maybe hands blocking their face, eyeglasses, no eyeglasses, different ethnicities, different ages, and they're not all framed the same. Some are tilted sideways, and there's a lot to work with there. And then if you want something in between, there's the Cone Canade plus the CK extended data set, which is primarily a video data set, but you can get still images out of it. And they're red, green, blue. So got some work and decisions there to make on, reducing it down on grayscale, but there's quite a few to work with there. And then what I did for the 2 demo models here, I did demos that use the JAFE database data set. I did get another one running that used the another method, but it was tuned to the FER 2013 data set. And before I put it in the presentation, I would have taken the time to make sure they were all comparing the same data set. I didn't see much point, even if it was working, comparing apples to oranges. So given those 3 data sets,
Sorry, pausing you, but one of the things that I just realized, what are the 7 categories?
Oh, okay, great. Yeah. The 7 categories are happy, surprise, sad, neutral, fear, disgust, and anger.
Yeah, I think you have it right somewhere.
Yeah, I've got it written down in a couple of the graphics, and then I had it. But yeah, those are the 7 categories.
The other question is, how balanced are the data sets? Like, how many are they equal in those 7 categories?
Yeah, I do have a histogram of both the JAFE and the FER 2013. The histogram, I don't think I put it in the report, but I think they were pretty well balanced. There was some distribution.
Okay.
And so, some models to start with. It kind of makes sense to start with a simple model just to prove the workflow, and going with SVMs, even though initially in the 60s when Vapnik and Chernovenkus laid out their paper on hyperplanes and decision boundaries. The SVMs began their life as binary classifiers. There's things that we can do to work with them and to become a multi-class classifier. And that's, so we start with, I decided to start with an SVM and then extending that to a multi-layer perceptron, going into kind of the next step up. It's not quite into the deep learning, depending on who you're reading and what they're saying. Most of what I've read, still considers MLPs to be shallow learning. It's close enough to that level. And then making the jump later, the next logical progression would be to make the jump into the deep learning. And so we'll see here some of the implementation of, before we can, after we've chosen a data set and after we've selected a model, then we still have to double check the data pre-processing. And in this case, we've got the typical things. We've got to get the data off the disk into memory. Sometimes they're labeled with strings. If they're labeled as strings, angry, ANGRY or HAPPY, there's going to be some, especially with an SVM, we're going to have to kind of numerically modify those. It's not really a lot to do. And then on the images, in the case of the SVM, we're just going to flatten the pixels right away. We're not going to do a lot of transformation. They're already grayscale. We do normalize the values. I think that if I remember right, the normalizing was pretty redundant. The normalizing it's useful to have in there in case in the future you pass in an RGB, but if you're starting with grayscale already, it's already 0 to 256, but it's there in it. And then of course we want to split it. What's that?
0 to 255.
Yeah.
Yeah, you're right. But it's okay. Yeah.
So then we need to split the data. And again, the Jaffe said it's kind of small, but we still, we're going to split it 80-20%, or 80-10 and 10 if we're doing a, test and cross-validation. And then it's always useful to actually spit out a visual output so we can test and make sure everything's functioning. And so a quick little display. You can see some thumbnails, a contact sheet of what's seeming to go into the algorithm as inputs. So this is a diagram that I put together for the multi-class classifier, the SVM. And so you've got each one of these is an SVM algorithm that's looking at a binary classifier. Something's either happy or angry. And then if nothing happens there, we go on to the next layer and the next layer until we get a hit. And then once we get a hit, then we travel down. And then, if it's, say we start with something that's a 4, and that first layer, it's neither 1 or 7. So we go down to the next layer and it's neither 1, 6 or 2 or 7. So we go down to the next layer and apply it to the next 3 kernels. And it's still nothing there. So we go to the next layer and then we're applying it to those 4 kernels and we get a hit on the first one. And then that first one feeds as we get a kind of a truth there on the 4, then we automatically, it feeds into the next, is it 2 or 4 versus it 3 or 4? And at the end we get a hit in the 4th class. And the idea is that these other classes will have 0 or low numbers of hits, and will, at the last step is to take the maximum value, which argument had the maximum value, and that becomes the output for that run on that. So that was all on one input, one face, and then that repeats over all of the other faces. And so a little bit of the code there on the running the classifier. took the default settings on the RBK. The only thing I looked at tweaking was the gamma and the C, the regularization parameter. And the next page will show some of the results of that. So with the initial configuration of just the default C 1.0, the default kernel, and the gamma of 0.001, got right off the bat without doing anything out of the box. We had a precision of 86%, recall 81, an F1 score of 80. Going through a grid search, giving it some different choices of C and some different choices of gamma, it comes back with these results of 10 to the -7 and 10 to the -6, and optimized. Our values do go up quite a bit. But the fear there is always, even though we've proven the workflow, the fear is we're still dealing with a relatively simple algorithm on a very small data set. So the likelihood and the risk of overfitting is to be expected, is probably high. So switching gears, now that the workflow, we know the data pipeline and everything is functioning correctly, you go in and try something a little more complex, MLP algorithm here. And right out of the bat, chose this is, so I followed a tutorial on this. I can't explain exactly the logic of why they chose to start with 2 layers, one of 1,000 nodes and one of 200 nodes, 2 hidden layers. But when it became time to do the optimizing and the grid search, to keep things apples to apples, I chose to keep the same exact number of hidden nodes, but restructure it with different layer and node combinations and see what that did. And so right off the bat, we get some results here, fairly not too far from the SVM initial results. We're 86%, 81, 80. The initial configurations, they're the first hidden layer, the second hidden layer, and the grid search, there's a typo there. It's not supposed to be SGC, SGD, and gave it some different choices of alphas. And then I gave it, I believe, I don't know if I have the code on the screen, but I think I gave it about half a dozen different layer configurations. Everything from the 1,000 by 200 to this one where it's evenly split, 6 layers at 200 apiece. And at the end, it came out with a 600, 200 apiece. The 6 layers at 200 apiece. And the final results, and we make a significant jump up. We're into the mid-90s now on the precision and recall and that F1 score. The next step, and again, like I said, I had a prototype of this running, only that it was running on the FIR 2013 database. So the next step would be to extend this and say either take the SVM and the MLPs and apply them to the FIR 2013 and look at the CNN at 2013, or it would be kind of it would be doable, but kind of a pointless exercise to apply the CNN to a 213 picture database of the Jaffe. You could prove that it functioned, but I'm not sure that it would really tell you anything worth knowing at that point. But this is a diagram I built that would you capture the idea of the sliding window going around, instead of just purely flattening the image right off the bat and just ripping the pixels into a straight vector. Going into this sliding window and taking these Polaroid snapshots of the grid as it goes across, and then reducing that down iteration by iteration by iteration until you get through that process a flattened layer. And then once we have a flattened layer, then we send it through the network of hidden layers, much like we did with the MLP. But in this case, these are the hidden layers are much more complex at this point. But the output is we still, at the end of the day, we're still looking at, the percentage, how much of it was likely that it was a happy, surprise, sad. We're still classifying these, and I don't have I could pull up on the, I think I sent you the Python notebook, but if you wanted to, I could pull up
This is fine. I was listening to you and the way you present and your confidence in what you're saying is all I need.
oh, well, I gotta tell you, I
need,
gotta tell you, working in a bubble like this, I don't always know where I'm at. So that those are really kind words, and it means a lot to me. I don't know how to compare where I'm at a lot of times. So I
well,
just really appreciate
the
it.
online is very difficult. That's why what you want to do, what you feel as an instructor is okay. When you show a presentation, when a student comes out with a presentation, when someone comes with a presentation, this is 2022, right? There's a lot of things you can cut and you can always copy and paste. But when they present, they cannot lie, right?
Oh yeah,
Just the details in what you're saying. I mean, it helps me assess how much of it do you understand versus what I wanted. Of course, I'm not saying it's perfect, but it does show. To me, it communicates. You understand what's going on. It's
well,
not.
I
I'm not
appreciate
going
it.
to go after the details, right? That's not what I'm doing here.
Sure.
But there's a depth to you, and I like it a lot. Actually, I'm very glad we did this presentation because.
Well, so am I. I mean, in all honesty, I haven't had anybody to talk to about what I do. So, I mean, my wife and my son can only handle so much, and it's just so it's quite nice to be able to share and discuss this with somebody who not only knows what I'm talking about, but then can give me the guidance of, hey, where am I at in my understanding?
A lot of the things you're saying, I mean, they reflect the right thinking. Now, I'm not saying I couldn't argue against. Yes, I could, but it's not wrong what you're saying. It's like there are issues with the data sets. There are issues with transfer learning. It's a data-driven world. I actually think Andrew Ng at Stanford basically pushes it all. It's all about data. I don't agree with it, but again, but the way you build it, it's like you build the right stuff. It's not necessarily state of the art or anything, but I still appreciate someone that builds things from scratch, even though simple, to see where the simple things go before you go jump and drop every new architecture on it. So I appreciate that angle that you took, and the fact that you're presenting nice confusion matrices, precision recall, so you've got it, okay? I mean, that's all I mean, I'm glad we're doing this.
Well, I really appreciate your patience. I only know one way to go about things, and that tends to be I go into a deep dive, and I just grind away and grind away. And so, I know in this case, in this semester, it meant, I missed the due dates on a lot of things, but you were really patient with me, and I think it gave me the freedom to learn it to the level I felt like I needed to learn it. That doesn't mean I'm by any means a subject expert, but what I know about it up to this point, I feel good about what I know about it. I know that it's just the tip of the iceberg, but at least I feel good about where I'm at so far.
Yeah, there is a maturity in your presentation. I like it a lot.
I sure appreciate that. So I believe that's now the last page. I was going to go ahead and before I turn in the last copy, I'll get the Python notebook links. They're on my GitHub right now. And I'll just polish up the links and get that all turned in here yet tonight. It's just a couple little edits. But
let me know as soon as it's turning. I'm okay. This is fine. This is